Hi, in the previous video, we derived this equation, right? And I said that if we can substitute this equation here, we should be able to get a relationship between V out and V in. And I thought that maybe it would be useful to just do this. So let's just try to work this out. So what we can do is, let me just separate the terms that belong to V in and V out and Vx, and just separate the equations out. Okay, so let's, probably the first thing that we can do is we can multiply the entire equation with zc times r. So you get zc v in equal to, and if you look at the vx terms, you will get zc vx, and again vx over r. So that becomes again zc vx, and then this term here, because we have multiplied it with ZCR, so this becomes RVX, right? So I can write this as plus RVX plus, now let's write the V out terms, or maybe it should be minus rather than plus. So minus, and we write ZC V out plus RV out. That's another term. And if you just pull the terms together, what you get is twice ZC plus R Vx minus ZC plus R V out. Okay, so now that we have this equation, and let's call this equation 3, what we want to do is we want to substitute for Vx from equation 2, and let me do that in the next slide. Okay, so I've just removed the circuit so that we can write out the maths, this arithmetic, and let's just continue solving it. So what I said was, what we want to do is we want to substitute for this Vx from equation 2 here. So if we do that, what do we get? So what we get is, so you have twice Zc plus R already, and Vx is Zc plus R over Zc, right? And that's V out now, minus Zc plus R V out. Okay, and now what we can do is, just if you want to further simplify this, what we can do is, we can take Zc plus R V out as a common factor, and what are we left with? You're left with twice Zc plus R over Zc minus 1, and you can simplify this, and that becomes actually 1 plus R over Zc times Zc plus R V out. Okay, and what is the left hand side? Left hand side is Zc V in, and that kind of gives you an equation, and now you can get V out over V in, right? And let's do the further simplification in the next slide. I'll just move the equations to the next slide. So here's the equation that we have, and what do we do with this? So let's try to simplify this and remove the denominator which is here, which is Zc. So you get Zc V in equal to Zc plus R times Zc plus R over Zc, right? And okay, let me just write that over Zc times V out. Okay, and this becomes equal to Zc square V in equal to zc plus r whole square v out. So what is this v out over v in? So v out over v in is given by, it's given by zc square by zc plus r whole square. Now what is zc? Now you know that the impedance of is given by of the capacitors is given by j omega c. Just to simplify and not bring the j omega terms into the equation for a moment, what we'll do is we'll just write this as, instead of j omega c, let's write j omega as s. Okay, and if you have studied Laplace transform, s is the Laplace variable, but even if you don't know anything about Laplace transform, that's fine. Okay, we're just going to do that substitution. And so what do we get here? You get 1 upon s square c square over 1 over sc. Okay, let's just write it as plus, oh wait a minute, that's not right. It's not it's 1 over sc plus r, and this is a whole square, right? And so what does that become? So let's keep this s square c square in the numerator, and what do we do here? So let's write it as 1 over src whole square divided by s square c square. And so this becomes 1 over 1 plus src whole square. Okay, and that you can, if you want, you can expand it. And what does that become? If you expand this, it becomes s square r square c square plus twice src plus 1. Okay, and one of the things that you can do is you can divide the entire equation with r square c square, so then you get 1 over r square c square divided by s square plus s times 2 over rc plus 1 over r square c square. Okay,